Sometimes in the laptop there's a function key to press Fn and transmit the string.
Yeah, on Windows used to be F10, right? So
Yeah.
But Mac doesn't have that.
Okay.
Another adapter I have mine. The one that I maybe work for you. So
oh, I don't need an adapter. I have HDMI.
Oh, cool.
Yeah.
If you need a USB.
if it presents something on a slideshow, maybe you can activate whatever. If you open PowerPoint and press something.
Yeah? No.
Yeah, try to initiate like a slide presentation or something. Maybe it triggers something that's not acting up.
So I can have the whole lot here.
Sorry.
We say
Sorry to ask.
I think it's the
Since you have a PC rather than a Mac, and did you download this?
Did you adapt to have DGA? Yeah,
Thank you.
Então,
Sobre tudo.
podemos tentar que.
You want to use my laptop?
I think it's the VGA adapter.
This one has a
Well,
HDMI
Oh yeah.
output. You want to try it?
One
I
second.
just want to also have HDMI, so you think it's the...
Maybe it's this one. But then it's
Here.
So you insert a USB somewhere?
Okay. So you can.
No, I don't have you.
Ah, but then.
Oh, you don't have USB? Oh.
We have an adapter. Do you want this adapter?
No, that's not gonna work. Adapter is gonna just
Yeah,
be
it's gonna
shitty
blow.
signal.
Do you want a USB-A to USB-C adapter? Yeah. Maybe this one helps.
Yeah, with VGA.
Yes.
Yeah, maybe
Yeah,
this
that's
one
better.
helps.
We have 3 or 4 adapters now.
How many engineers does it take?
How many adapters does it take?
Amazing.
That's the USB. That's not going to work. But, so the way to use it is not with the HDMI here, because if this is just USB, it's not going to pass image, right?
I mean,
Yeah.
So
I use this adapter, yes. I use exactly this adapter, yes. With this. I use HDMI, but the USB is connected to the laptop, right? So
Yeah. No HDMI.
I connected the USB to my laptop, and then I use the HDMI port.
And usually you use something like this.
So you need this.
We have to keep track of all the adapters. Ah, it works.
It's
magic. It's for Mac, right? So it works everything Apple. It's like perfect.
Okay, sorry about this delay. It was about technical stuff. We are now starting the parallelization 2.2. Start processing background and methods with Simon Lupemba, that is a junior remote sensing scientist at EUDMETSAT working on the scatterometry team. He supports the quality monitoring, calibration and validation of operational scatterometer products, and also prototype and maintain processing software for the extraction of products. He is an MSc graduate in Earth and Space Physics and Engineering from DTU and have hands-on experience working with SAR data from his studies. Most of his academic projects focused on processing SAR images, such as speckle filtering, interferometric currents, and automated flood mapping. He have implemented in-SAR coherence processing in Julia without using commercial software or SAR-related libraries. And he also have worked as an IT consultant at Net Company for 2 years, where he was involved with supporting maintenance and development of medium-sized public IT projects. His regular tasks included defining and estimating tasks, developing new features, fixing existing bugs, and providing general support. We'll also have Heigl Lippert, and is currently pursuing a PhD in numerical glaciology, in which he is working with the reconstruction of the Greenland ice sheet and its glaciers, going back to the last little ice age. This work is mostly centered around finite element modeling of glaciers and trying to understand their main drivers and dynamics. Before this, he did a master's degree in engineering focused on Earth observation data, large-scale learning. He was also involved in satellite observation and analysis and developed a method for synthesizing landslides in the in-SAR coherence domain, and also building an algorithm that could detect these signatures in real-world SAR coherence data. He also developed an in-SAR coherence processor in Julia, which could process SLC data and create interferograms and coherence estimates. He is currently in the process of porting this work into an open source library, together with 3 other people. Okay, thank you.
Yeah, thank you. So I'm Michael, and this is Simon. Thank you so much for the presentation. It was much better than I could have done myself, I think. So me and Simon, and also Christian, who's down there, we went to the same university and worked on SAR processing together. And basically, we decided to start trying to make this a proper open source package in Julia with some of this work, and also hopefully add more work in the future. And that's called sarprocessing.jl. Yeah, that's good. Yeah. So even though many of you here maybe know already a lot about SAR, we hope that it's okay. We'll just recap a little bit of the basics. Also, Felix talked about this in the morning. We'll try to keep it a bit short, so it's not too much. But then we'll go more like into a little bit more detail with the in-SAR, which is a bit more uncommon to a little, like a few people know SAR and a little bit less people know in-SAR maybe. And then we'll just finish up talking a little bit about the state of the project we are working on, like the package. And and then we have a hands-on session later. And Friday we'll talk even more about the package itself and like what we envision with that. Yeah. So, as some of you know, or also as Felix said this morning, one of the main kind of value propositions of using SAR data is that it's pretty good for time series because it's not affected by clouds, and you can use it even though there's no daylight. So, for example, in this case in Greenland, half of the year you don't have daylight, so you can't really sense anything unless you're using something different than optical sensors. So in this case, SAR is really useful. Can you change slide? The basic principle is like the SAR is sending out an electromagnetic pulse that's then reflected on the surface, and there's different situations. So one is like that it's reflected directly away from the kind of source of the signal, so you don't get any reflection back. Basically, you don't get any backscatter, you don't get any signal back. And there's like other cases where it's more complicated. You get something back, something is sent away. You can also have really strong reflections. And that's kind of the basic kind of dynamic of the SAR. And these cases actually, I don't know how clear they are to you, but this is kind of a forest, and this is an ocean, and they're kind of similar to what would happen in real life. In the ocean, you get like very little signal reflected back, and over foresty areas, you get kind of a mixture of signals getting back because it depends on the geometry and what the surfaces you're hitting with the pulse. Yeah. So it works in the microwave part of the electromagnetic spectrum, and as Felix also mentioned this morning, there's different sensors in these different bands commonly. we are kind of mainly going to talk or like assume that we're talking about Sentinel-1 because that's the main sensor we've been working with so far, like programmatically. But they have like different pros and cons depending on like what sensor you're using. For example, like some, they can look through clouds, but some of them can also look like through different types of vegetation. As Felix also had this nice small plot of earlier with the different canopies you could kind of penetrate into with different levels. Yeah, next slide. All right, and the electromagnetic pulse is a complex signal. It exists of an amplitude and a phase, and depending on what you want to do, they can be interesting. Like, so you can both work with the amplitude and the phase. They contain information in a way, but you need to process them differently to get information out of them. Most people work with the amplitude because it's a bit more easy, easier accessible. And the phase is like something you process in the INSAR processing chain, which is something we'll go more in depth with in a second. And that's, kind of interesting what you can do with that. And then, in addition, the SAR has kind of polarized signals, so it has both a horizontal and a vertical polarization. And that just depends a little bit like on how you set up you can kind of decide what polarization setup you want for the return. Yeah, next slide. Yeah, so just to come back to this was just to say that there's a lot of factors coming into the reflected signal and what you actually see. So both the surface, like the band you're looking in, the band of the electromagnetic pulse, and also the geometry, like what the geometry on ground is, and like the topography, also the viewing angle and stuff like that. And all of it comes into like the actual output of the observed map. So if we go on to the next one. Yeah. So just a little bit about the geometry. So, and this is going to be this is quite important in the whole INSAR processing chain, that this is pretty clear, like when you're developing these things. Also when you want to analyze SAR data in general, I guess. But so basically we have the SAR, which is mounted on some platform up here, and it could be a satellite or a airplane. In this case, we will just assume it's a satellite, but it doesn't make a big difference in terms of the geometry. And it flies in this case, it flies in the x direction, and it looks in the y direction. And it has some velocity. That's kind of the basics. And you can see it covers some area, which is called a swath. And it can kind of steer its antenna in different patterns. It depends a little bit on how it's set up. The Sentinel-1 has a very specific steering pattern, which you have to account for in the processing. Yeah, so if we could take the next slide. So if we look at this from the top instead, I don't know if it's... I don't know if you can see it. Maybe you can see it.
You will get a chance to see the images much better on the hands-on sensor
yeah.
when you have them on your own computer.
What do you want to do?
We could change projector to black because it's not very useful for whoever is online.
It's up to you.
Okay.
If you want.
Yeah.
Do you mind having a...
No. It's good. I also talk to fast.
So there are any challenges of acquiring it over the ocean, or the sea? You mentioned that you have to have the scattering back, right? But is there any challenge of actually?
I can I work with radars over the ocean, and it's actually really good because when you get the signal back, it really much depends on the ocean roughness, and so if you have a very calm ocean, you have very little signal, but as soon as you start to have wind and get waves, then the signal increases. And that's actually used operational in scatterometers, which is a quite similar setup to SAR. It's just way larger pixels to get a better backscatter resolution. And that is actually like one of the main ways that you retrieve wind speeds over the oceans for global weather models. So it can be when you're analyzing assignments and looking for ships, it can be really annoying that patches on the sea can be very bright due to wind and there's this variation. But it is also useful if your goal is to retrieve wind and waves.
You can see an image later in the hands-on where we have like increased intensity, so you can see like the patches on the ocean.
Nice.
Um,
What about the sea floor? Like, can you go all the way down, like very deep, or?
No.
And so the thing is that
Qual são os comentários, faz favor?
Qual projetor?
Já está
the
ligado.
microwave radiation is reflected on the sea surface, and it has a very tiny penetration depth when it comes to water. So like you don't see anything. But a fun thing with SAR is that some wavelengths it can actually penetrate some dry soil, so like sand or snow. But I haven't worked with that. But not water. Water is completely reflected. Right.
Do you remember the PHA use case with the seagrass or something? What did they do with that?
It was optical.
Optical, okay.
you can see the sea somehow if it's low enough. 10 meters down.
We might need to reposition it in that.
Ele não entendeu bem? Sim. Tenta começar a ver.
Projeto é no teto.
Não. É short throw, por isso tem que estar próximo da parede. Não, tem que se aproximar da parede. É só isso.
Aqui é corrente elétrica. Aí, essa extensão pode vir, exatamente. Essa pode vir.
É em cima.
Aqui?
Sim. Mas pode pôr mesmo junto à parede.
Way there.
Olha,
False
em
colour.
negativo. Está em negativo.
There's something with the colors. It's supposed to be a white.
Já sabes trabalhar com isto?
Aí é uma não.
Está em negativo.
This is the signal, not the projector.
You think so?
Yeah,
There's another port on the side.
because the UI of the projector is displaying the colors correctly.
Yeah, good point. There's another port on the side, HDMI, yes.
Might be the wire.
Didn't we use the same wire for the other one?
No.
No.
Não, vai, mas este vídeo que ele dá atrás do motor.
Same.
Or the cable or the connection. Over there.
Olha, mas não tens
By
ainda
changing this.
as definições do projetor.
It's still no,
Yeah, it's
it's
better. This is good enough for me, I mean, but
Yeah, let's move on. Yeah.
Está
Here it's
fixe.
better.
Olha,
Online is better.
exato. Sim, está melhor. Mas podes pôr mais para trás para isso ficar maior um bocadinho ainda. Tipo um bocadinho para trás. Exatamente. Olha, perfeito. Nunca pode ser assim.
Está equilibrado?
Tá bom.
Okay. Okay. Can you see? Yeah.
Yeah.
Okay. Okay, so we got to this. I'll just kind of start, if not over, but just start. So just to recap, this is a geometry when you look from the side, and you have, like, it's a bit random, but this kind of sketch is called X and Y. And I just wanted to kind of connect that to this image. So I have Y and X, so it's just swapped. So basically, we have the flight direction in this direction, and the size looking this way. And actually, I just noticed when Felix showed this earlier that this is the kind of radar geometry version. So it's flipped with respect to reality. So this volcano over here, it was on the other side in Felix's image. So I think, but it's because for our purposes, we are kind of working a lot in like the SAR geometry as most of the time. So we haven't really, we are not really at the point in the processing we're doing where we need to like flip things and make things correct in the real world. But anyways, that's some of the kind of details. And then also you get backscatter patterns that you see high backscatter from the kind of mountain ranges or cliffs or whatever that's facing in the correct direction, so to speak, to get high backscatter, and very low in the ocean, and also low in like these more flat or vegetated areas. Yeah. Right. Well, this is a bit hard to see actually, I think, but you can kind of sense a little bit up there, some red here, right? And a little bit more green. That looks like lighter colors to you maybe, but basically it's just to illustrate that if you look at the kind of intensity or the amplitude of the VV signal and the VH, so that's if you send out the signal in vertical polarization and receive vertical, or you send out vertical and receive horizontal, you get like different intensities, different different places. And this also comes a little bit back to what we heard earlier, that these have different sensitivities to different types of kind of land covers, or like what they're actually hitting when they hit the ground. Yeah, and then Simon will take over and talk about the INSAR part.
So I'll just give a short introduction to interferometric synthetic aperture radar. So that's INSAR. And I think the first slide here is just to show that we have this SAR image which is recorded by the satellite, and the satellite receives the complex signal. So this is from Sentinel-1. So here we have the real part of the complex spectrum and the complex image, and here we have the imaginary part. And it's not just a projector, there's something wrong with it. It looks like noise. And that's because...
It all looks like noise because we can't see any differences.
Yeah, but it is also noise, even though you zoom in. But the thing is that if you... Yeah, it all looks like... But it all looks like that. But here, you will actually be able to see some fields and some structures in the amplitude of a single image. And
if you download the notebooks today already, if you go into the INSAR hands-on thing and open the first notebook, there's a link to the slides engine. Just so you know, if you really want to look closer, you can do that. Sorry, go ahead.
Okay. And here we have the face, and the face of a single image is just noise. But we are able to get information out of the face if we combine multiple SAR images over the same area. And that process is called INSAR, where you're actually exploiting that this face is not like completely random. The face is complete, but if you look at the difference in phase between two images acquired almost from the same position, then you can retrieve information from the phase. And that part is the INSAR process. Yeah. So we look at the phase difference. It's the same. So the way that this is done is that you take a SAR image by one satellite and a SAR image by another, and then you can process it and look at the phase difference, and that is normally plotted in this nice color map here, where you have the phase changes. These phase changes correspond actually to a difference in range for each pixels from the two SAR acquisitions. So it is such a way that the image is taken by one satellite at a given time, and then maybe it's taken by the same satellite again at a time slightly later. And every changes in range between these satellites, like the distance the pulse have to travel, will result in a phase change. That is useful for different applications, because you can use the phase shift to do a topography mapping. So if you have an area where you don't know the topography and elevation, you can use this to generate digital elevation models, which have been used. But if you know the elevation of the area, you can subtract the digital elevation model, and then you can get out the surface deformation, which is also widely used to monitor changes in the surfaces. Yeah, and just some small formulas, but this is just to say that the coherence would also has the phase that is shown in the plot, the interferogram. It's you take one image and then you multiply by the complex conjugated of the other image to get the phase, and then if you also want the magnitude of how well these phases correlate, you divide it by the magnitude. So you kind of get a scale in magnitude from 0 to 1, and you have a phase that corresponds to the deformation. This coherence parameter is often used to see if the surface is stable. I have the formula here, so I can mention it now. So the phase change is due to a lot of different terms. We have a phase change just due to the different position of the satellite. So if we imagine the Earth was completely flat and we had two images over the same region, the satellite will not be in exactly the same location. That change in location creates a phase turn, and that creates some ripples, which can be calculated easily and removed. Then we have the topography. It can be extracted if that's like what you're after, but also it can be removed. Then you have a term due to the deformation, and that is for many applications what you're going after. But then there's also some others, so like atmospheric, like changes to the atmosphere can cause a signal because it changes the speed of the radar pulse, which can actually cause like a slight phase shift. And then you also have all things related to if the surface changes. So this INSAR requires a stable surface. So the kind of principle is that a stable surface, you can look at the phase difference there, but if you have a surface that's unstable in the time scale that you're operating, so water is like a common example, you cannot get any useful information out of the phase, because the surface structure will have changes from one image to the next image. And then the phase change is related to a change in distance, and I think what is to say is that it depends on the wavelength of the radar. So you can actually extract really small changes in range, even though the resolution of each cell may be like 30 by 30 meters. When it comes to if the 30 by 30 meter pixel have moved, then you can have a resolution of centimeters and see small changes.
1 second. I just want to see if I turned off this. It won't help. No, it did not.
Sorry.
Ah.
I think it's also you now. No, I have one. So, like to create this interferometric INSAR, there's several processing steps, and we will go through some of them in our hands-on session. This is a plot of some of them. It's a figure. It's a little bit of old figure, so it's not so streamlined. But the idea when you do this is that you have one image that's acquired over the area, and then you have the second image that's also acquired, and then you will have to take the second image and resample it to the first image so the pixels align pretty much perfectly, because any misalignment between the pixels will cause an artificial signal. So the way the processing is done is that first you take the information from the primary image, and together with that you also need to know some precise information about the orbits of the satellite. And you take that together with a digital elevation model, so you know the topography. Then you convert the digital elevation model onto the geometry of the primary image to get the heights of the pixels. Once you have the heights of the pixels, you are able to transform them to coordinates, and then when you have transformed the positions of the primary image to coordinates, you can transform them to positions in the second image, and here you are able to resample the second image, stack them on top of each other, and then you can start the INSAR processing. So this process can be quite tedious, and there's a lot of small things that you have. But we will step through this process during the hands-on session. Yeah, and then just an example of some. Here we have an interferogram over the west coast of Denmark, and here we have the corresponding coherence that says something if the surface is stable and if you're actually able to use the phase information. And what we see is here we have water out here, and the phase of the water is just noise. But over land you see a more clear phase change. In this case actually it's only made from a single image. The phase change is most probably due to changes in the atmosphere between the two acquisitions. But you can imagine if you average out like a lot of acquisitions over the same area, you can compensate things like the atmosphere and more get if there's like a trend in deformation happening. Yeah, maybe shorten the application.
Yeah, so there's just some examples for.
But should we skip it?
What?
So how's the time with the hands-on session? Do we extend a little bit? Or?
I suggest that I think the best option will be to finish here on time.
But how much time do we have left?
None. And then you could do the other one, extend the other one. So finish this one downstairs with everyone, and then do the next one, because there's no interval between these two sessions, right? The other one is also SAR. It's with Simon and Christian. So you could, if you wanted, that's an option.
But is the hands-on here?
No, downstairs with everyone.
Should we maybe just do the SAR
Let's finish
process?
this presentation here, when we started here.
Yeah.
4 slides.
Just take your favorite application.
Yeah. Okay, you can measure ground deformation. This is an earthquake. You can kind of count the fringes, and then you can get like this is deformation in meters. So Simon only talked about the phase deformation. That's not like a phys. It doesn't have it. You have to convert it into something that is a length unit to get something, and you can do that. This is not my work, so. But basically, you can use it, and you can also see up here that maybe even the earthquake was really violent, or there's vegetation, so you get noise. But here you can actually measure very accurately like the deformation. So each of these kind of fringes, that's kind of one color bar, so to speak, that's called a fringe, corresponds to like 0.028 meters. So you can kind of count up how much deformation is. You can also measure, that's pretty cool. I use this data a lot actually for the glacier modeling. That's a slow moving part of the ice. You can measure the surface velocity with INSAR. So there's some methods to convert this into ice surface velocity. And then also very cool application. They actually did this over all of Europe. There's an Italian company called Altimeter. I don't think this is their work, but they did that. So basically you can find persistent scatterers in an image that could be like a roof that's always giving the same reflection. And if you measure that over time with INSAR, you can kind of get out the deformation of that roof. So maybe if the building is sinking down over time or elevating or something, you can get kind of subsidence in very precise measurements actually over long time scales. Yeah, and then we just wanted to introduce a package, but we can maybe just do this later. But one thing that would be nice to maybe just finish up with is like if you have time before the hands-on session, you can. So if you pulled everything from the USB drive today, like all the folders, like you're fine. If you only pull the data, you miss our data actually. So you either have to get the USB again, or you have to go onto our GitHub. Where is it? Yeah, go onto our GitHub, and we can show you where to find a link to download the data. And then also you can do yourself a favor by opening the first notebook. It's called Load Image, and just add our package basically, because you need to install it. It takes, if you don't have any of the dependencies, it takes like 5 minutes. But so it was just kind of a small, you save some time if you do this in advance. I think that's it, right?
Yeah. I think so. We will leave the rest for the hands-on session. And yeah, what I want to say about the hands-on session is the package is a place between being a finished package and being a proof of concept. So there's still a lot of work to be done, but that also means that we can go through each step in like the processing chain and like see what's happening.
Thanks.
Thank you.
Okay, thanks so much. We are really sorry about the technical issues. Hopefully downstairs things will work better. And because there's a coffee break afterwards, so you can extend by 20 minutes. Okay. I think it's better than trying to force it here. It's not working.
Ja. Men jeg tror måske, vi er nødt
Men lad os lige, hvis det er så... bare fordi skal lige selv huske på det der, der godt kan være en lille tænkepause for folk med deres rapporter, så der ting i 2 timer. Selvom vi bare kan trække ind i kaffetræet.